All right, so let's keep going with limits. We are right now in 1.3, part of the way through. And so what they're doing here is they're showing us that sometimes it's not obvious how to solve for a limit, and there might be strategies that we can follow to help us identify techniques that we might use to solve for a limit. Now, one of these, interestingly enough, is to see if we can find a function that is identical to our function, except at possibly one single point. Okay, so that sounds like an interesting strategy. So here, for example, we have two functions, f of x and g of x, and in both cases, we are looking for the limit as x goes to c. And but what we do have to pay attention to here is that um, the two functions are identical except at c itself. Okay. So in other words, they're identical except for that one point where they're different. How does that help? All right, well, let's take a look. Now, you might recognize this one. We did this one earlier. The limit as x goes to 1 of x cubed minus 1 over x minus 1. Okay, so you'll recall that this one has a hole in it at the point we're looking for. And in fact, the symbol lab graph might even still be here. Oh, maybe not. I'll just start it again. The chances of it still being there, you know how it is when you're around the computer all day. Um, so it is, what is it? X cubed minus 1 divided by x min minus 1. Okay, now remember that we graphed it and there was a hole at a single point, and that point is x equals 1. And that's, of course, because if we let x equal 1, we'll have division by 0. So that's the point of interest. The point is 1 comma 3, although right there, that exact point is not part of this graph because 1 is not part of the domain of f of x. Okay. So what they're going to do here is to point out that we could take the same function if we wanted to, and we could actually factor it out. So what would that get us? All right, let's find out. All right, hold on one second. I just realized I never set up a set of notes here. Okay, let me just get this set up. Okay, so in other words, if we start out with f of x equals, often what happens when we have a rational function like this, and remember, a rational function simply means that we have a ratio of two polynomials. And there's always a possibility that the denominator divides evenly into the numerator. In other words, it's possible that x minus 1 could be a factor of x cubed minus 1. And if that's the case, we can simplify the entire expression into something more manageable. Now, you might say, well, I'm not sure. It's hard to tell. And that's absolutely correct. But you may recall, though, there's a technique you can use to divide one polynomial into another. And I'm just going to briefly run through it with you in case you haven't seen it in a while. And it kind of reminds us of long division. And so here's how it works. And if you figure out how to do this, this is fine. We have x cubed. Now, in order to use this technique, we need to have some placeholders here because x squared is missing and x is missing. So we'll start by multiplying this x minus 1 by whatever it is we need. to eliminate x cubed. Okay, so in other words, I'm going to choose x squared because x squared times x minus 1. Let me write this down here somewhere. Um, Someplace where I don't want it to get in the way. Hold on. Yeah, that's better. Okay. Okay. So if I multiply x minus 1 by x squared, I'm going to get x cubed minus x squared. So now I'm going to subtract. But I have to be careful because I'm subtracting both terms. That means this becomes negative x cubed. This becomes positive x squared. These cancel out, and I'm left here with x squared. Then I bring down whatever was next, and I try again. So this time I'm going to pick an x. Why x? Because if I multiply x by x minus 1, I'll get x squared minus x, which I now subtract. And what does that leave me with? Well, the x squared and the negative x squared drop out. So remember, this now becomes a negative. This becomes a positive. I bring down the negative 1. So I put a 1, and of course, 1 times x minus 1 gives me x minus 1. That's perfect. That's what I needed. Subtract, add. And so what this shows me is that indeed x minus 1 is a factor of x cubed minus 1. In other words, this ratio equals x squared plus x plus 1. Okay, now if I graph this one in Symbolab, we're going to see something very interesting. I don't think it's really feasible to do them all both together at the same time. So I'll just remember we have this hole at 1 comma 3. This time we have x squared plus x plus 1. And aha, now you can see, well, it's hard to be sure, but the bottom line is the hole is gone. Okay, I mean that's what this is all about. Okay, so that's why we're doing this, because we want to see. Okay, so here we had our original function, x cubed minus 1 over x minus 1. And then let's copy this over here. And the new function, which is the same function, we don't have to worry about division by 0. So x squared plus x plus 1 doesn't have a hole. We can just fill it in right here. And so what this means, and by the way, these both, don't forget, these take place at 1. Hold on. Yeah, we don't need this. So what this means is that the bottom line, after all that, after all the dust settles, is that the limit as x approaches 1 equals the limit at that point. Only at that point. That's the only place we're guaranteed that they're the same. And so therefore, this one on the right, we can easily solve for. So here we have a 3, and here we have a 3. So the limit in both cases is equal to 3. So in other words, what they're saying is that if you started out with this one, which we did, you would discover pretty quickly that there's a discontinuity. So what you can do to find the limit is say, well, listen, let's find another function that doesn't have a discontinuity, but is identical everywhere else. Therefore, the two must have the same limit at that point. So that's what this part is all about. And so, yeah, so they went ahead and proved it. So the ones, most of them, you'll see, and we saw earlier that we can often find limits with direct substitution. And the ones that cannot, possibly we can find another function that is identical except for that one point, and then use that to find our limit. Dividing out technique. So here, well, we have another problem on our hands. We have x squared plus x minus 6. Okay, limit x goes to -3. This function is x squared plus x minus 6, and the denominator is x plus 3. So what we'd like to be able to do, oh, I almost forgot. We need page numbers. Let's graph this in Symbolab. We want to be able to visualize what it looks like. And let's see what that turns out to be. X squared plus x minus 6 is divided by x plus 3. All right, let's take a look. Huh, interesting. So remember, we're trying to find the limit when x is equal to -3. That's right here where this hole is. Okay, it's undefined at the point -3, -5. So what are we going to do about it? Well, once again, we may be able to factor. In fact, it looks like we are able to factor. So factoring is something you might not have done for a while, but what you might want to remember is that, let's say we have a polynomial like x squared plus x minus 6. It gets like this sometimes. I've noticed it gets into these moods. Anyway, let's ignore it. Um, so how do you factor this? All right, well, just in the most general terms, here's what you're trying to do. You're trying to break it up into two binomial terms, which we could write as x plus m and x plus n. We don't know what those two are, but what we do know is that if we multiply these out with FOIL, we'll get f first here, o is these two terms, and x. I would be these two, inner, and then finally these two would be the last terms, mn. And when we bring these together, you'll see that we can line these up with the coefficients of our expression and solve for them. All right, so we have, which means that this must equal 1. There's an implied 1 here. And this is equal to -6. So what we're essentially doing here is solving for simultaneous equations. We need two terms whose product is -6 and whose sum is +1. So what we're going to do is try the different integers whose product is -6. And we'll just keep making our list until we find the one where they add up to 1, which would be this case. Okay, so if I choose m to be -2, n is 3, it's pretty clear that m plus n is 1 and mn is -6. So that implies that the original expression, x squared plus x minus 6, is the same thing as x minus 2 times x plus 3. And you can confirm that with FOIL if you want to. So what that means then is that if we come back here, aha, look what we can do. We can rewrite it as oh my God, it's just x minus 2. Now, of course, we also could have used that long division approach that I showed you a few minutes ago. That is also on the table. But what we ended up here with is the result that this limit is the same as the limit of x minus 2. And now we just use direct substitution to come up with -5. And you can see from the graph that in Symbolab, that's exactly right. Oh, where is it? Right there. Yeah, you can see when you hover over these points in his Symbolab, it shows you what they're equal to. -3, -5. That's exactly what we were looking for. And we are in effect using the same technique because we've reduced this ratio into a very simple linear function, which does not have any discontinuities. Okay, so once again, because we know that these two are the same, except when x equals -3, they must have the same limit at x equals -3. Okay, so that's what this is all about. So the final answer is -5. Okay, and yes, and they've got their own graph there. Okay, Now, sometimes we run into this case. Of course, we know not to divide by zero, but once in a while, um, you end up with a result after substituting the limit of 0 over 0. Now, that's pretty terrifying when you see it. We call that an indeterminate form. And that just basically means that direct substitution leads to a limit. Now, I do want to point out there's more than one indeterminate form. Um, you could, for example, and we'll see this later on, you also potentially could run into infinity over infinity, and that would also be considered indeterminate. But the way you resolve this could be different. But the word indeterminate simply means something really bizarre, like 0 over 0 or infinity over infinity. When that happens, there's a couple of options. One of them is just to algebraically rearrange it so that this is no longer the case. And at the moment, that's all we know how to do. But there's another technique we're going to learn a couple of chapters that gives us another way of handling these cases. Like here's a good example. Let's take a look at this one. So here we've got a problem because direct substitution gives us 0 over 0. Let's prove it. Oh boy, that's exactly what we didn't want to see. So what do we do about it? Well, every case is a little different. Okay, so what are we going to do with this one? All right, we have a very special technique that we can use, and it's called rationalizing. We're going to do something called, in this case, the numerator. Because the way things stand right now, radical x plus 1 is an irrational number. So here's what we're going to do. Now, if you notice, the term on the right that I've just introduced is equal to 1 because the numerator and the denominator are equal to each other. The question is, why did I choose that particular form? Because the way it's set up in the numerator, this will get rid of all the square roots. Okay, so first let's do this. Let's multiply across the numerators. And since these are both binomial expressions, we can use FOIL. All right, so F. Now here we're multiplying these together. When you multiply two radicals, you'll end up with just very simply x plus 1. So that's F. O, would be here. I would be here. And then last is these two, -1. So look what ends up happening. The two terms in the middle will drop out. So we end up ultimately with x plus 1 minus 1 equals x. Great. So our numerator becomes x. What about the denominator? All right, let's do that real quickly. Oops. All right, so it's x times radical x plus 1 plus 1. All right, let's do that. So here we have x times radical x plus 1 plus x. All right, so now we're going to combine these. All right, so we're going to substitute in the results that we just found. So remember, the numerator reduced very nicely to x. The denominator is x radical x plus 1 plus x. But if you notice, every one of those terms has an x in it. Um, Actually, what I should have written here is not that it equals that, it equals the limit. Hold on one second. Okay, so every one of those terms has an x in it, so they'll cancel each other out. And we're left with 1 over radical x plus 1 plus 1. Now we can directly substitute the 0 in there. It's a half or 0.5. All right. So in other words, we took a messy expression where direct substitution led to 0 over 0. And by rationalizing the numerator, we ended up with a very simple result, which is 1/2. Now you can see, obviously, you need to have a lot of practice in order to notice these things. I mean, it's not going to jump at you right away. You're going to say, wait a minute, what am I supposed to do here? Well, this is the thing about calculus. You can learn it with practice. If you keep running into these different cases, eventually you'll start to get good at identifying them. So when you see like something in the numerator or the denominator with square roots like that, that is going to be something you should consider as a possibility for solving for the limit. All right, and that's what it looks like. And you can see there is a hole there. So now the squeeze theorem, this is going to be a little tricky to apply it, but sometimes it works well with trig functions. What they're basically saying is that if you have two functions, three functions actually, let me just grab a copy of this so you can see what they're talking about. This requires us to find that essentially surround the one that we're looking at. All right, that may not be easy, but it could work well with trig functions because of the way we've seen before that they look like roller coaster rides. That kind of thing. So our function is f, and if you notice, there's a function g that is always everywhere, at least it's above or possibly equal to f at this one point. And then the opposite is true for h. You've got h, which is always below f, except possibly at this point. And what this means is that all three of these have the same limit as x equals c, converges to c. So because of this setup here, they must have the same limit. So you might be able to put this to good use if you're looking at a very tricky limit, one that leads to division by zero or possibly zero over zero. You may be able to take advantage of the squeeze theorem if you can find the other two functions. Okay, so let's see what they came up with. Um, oh, okay. So I guess what they want you to do is possibly use these. Um, I, oh, I see what they're doing. They're saying, here, try these. All right. They're giving you a hint that you're going to need these two. All right. Let's write these down. The limit as x goes to 0 of sine x over x equals 1. And then the limit of as x goes to 0 of 1 minus cosine x equals 0. And then what they're saying is, well, given that information, let's try the following. Tan x over x. Okay, great. Now, if you have your calculator right there, um, the tangent of 0 is 0. Okay, I just want to remind you about that. So direct substitution will put us into big trouble because you can see we'll end up with 0 over 0. But you'll recall from a couple of sessions ago that the tangent of x is the sine over the cosine. Well, how does that help? Well, let's see what happens. So we'll rewrite it a little bit. By the way, this is a good opportunity for me to remind you of something extremely important. If I take a ratio of any real numbers Dividing by C over D is equivalent to multiplying by the inverse, which is D over C. So therefore, in a case like this, we can think of this as sine x over the cosine of x divided by x over 1, which in turn is the same thing as sine x over cosine x times 1 over x. And that means it's equivalent to sine x over x cosine x. Okay, so in other words, this expression here is equivalent to now you're saying, well, how does that help? Because if you look at the functions that they mentioned earlier, these two, we could rearrange what we have algebraically and turn it into something like this. All right, let me just copy these so we don't lose them. All right, so this, whoops, what do we have here? Limit x goes to 0 of sine x over x cosine x. Let's see. We can write this as yeah. Well, clearly they mean for it to go. So how does this help? That's the big question. All right. So in other words, this limit, which if evaluated directly would lead us to 0 over 0, which is an indeterminate form that we don't want. After all this algebra, you can see that we could rewrite this as sine x over x times 1 over cosine x. Now, the first one, and by the way, remember from earlier when we saw how the properties of limits are such that the limit of a product is the product of the limits. So, in other words, we could rewrite this as the limit of x goes to 0 of sine x over x times the limit as x goes to 0 of 1 over cosine x. And now this one at least is one of the two cases that they gave us in the slides. If you come back here, you'll see there it is. So that's very helpful. So therefore, this part is just 1. What about this on the right-hand side? Well, this one can be solved with direct substitution because if you look at your calculator, you'll see that the cosine of 0 is 1. And so the product of these two is one, and that's our final result. Okay. So, this time it was the trig functions that we needed to know. And of course, it helps that we have this. If they didn't throw this little hint our way, we might not have ever figured it out. But again, after a while, you'll get plenty of practice, and you'll start to get a feel for how these work. So when you see the limit of trig functions, there will be some identities that potentially could come in handy to reduce it to something more manageable. Let's see, what else do we have? And this is a graph of what we were just doing. And so, all right, well, here's one they want us to practice. So let's give it a shot. Oops. All right. Now, first things first, clearly, based on what we've just been talking about, this will almost certainly give us an indeterminate form, but let's prove it. Yep. Well, that was pretty clear. So what do we do about it? Well, probably our best bet is to factor the denominator. And if you look at it closely, x squared minus 64, it turns out that this can be factored into x plus 8 and x minus 8. Okay. So whenever you see a quadratic equation or expression like this, and you see that there's no x term and the constant is a perfect square, which in this case means x 8 squared, and it's negative, then the chances are it can be decomposed like this. So we end up with x plus 8 over x plus 8 times x minus 8. And of course, the purpose of doing this is to cancel out the x plus 8s. Oh, I just realized I wrote infinity here instead of 8. Sorry. Hold on. All right. So once again, it's the limit as x goes to negative 8. And so now we can use direct substitution. 1 over negative 16, or sometimes we just write it as negative 1 over 16. It's the same thing. All right, so let's go back to the slides and we'll see that we've clearly, well, our guess is A. Okay, and the answer is on the next slide, and it is, in fact, negative 1/16. Okay, great. All right, so now we're ready for 1.4, which is the last part of this chapter. Let's see what that's all about. Continuity and one-sided limits. Yeah, continuity is a huge deal in calculus. The idea here is that if a function is continuous, that means there are no breaks in the curve. Okay. So, but of course, we need to be able to prove it more formally than that. And so, informally, as it says here, to say that a function f is continuous at x equals c means that there is no interruption of the graph f at c. Okay. No holes, no jumps, no gaps, nothing. It just goes straight through. Now, here's some cases. Let's take a look at these where the graph is not continuous, and let's see why. Okay, so the first one, f of c is not defined. There's a hole there. So over this interval from A to B, there's at least one point where the function is not defined, and therefore it is not continuous over that interval. Now, in the middle, you can see there's a gap. And we know what that means from before. The limit as x approaches from the left, c that is, of f of x would be this value here. And the limit as x approaches c from the right would be this value here. And you can see they're not equal to each other. And therefore, the limit of f of x as x approaches c does not exist. And that in turn means the function is discontinuous at that point. Okay. And then here, now look, this is kind of interesting. There's a hole in the graph, but there's also a hole. I mean, sorry, there's a point here. So in other words, what this is saying is that this is a smooth continuous function, except here, where there's the sudden jump from the hole down to the solid circle. So the limit is here. Hold on one second. So the limit does exist, and it equals this point. But this is f of c, and they're not equal to each other. And again, that's enough to conclude that the function is not continuous over this interval. Okay, so there's three ways in which the function can be discontinuous over an interval. Number one, it is undefined at a given point in that interval. Number two, there's comes a point where the limits are different on the left and the right. And number three, there is a limit at that point, but it does not equal f of c. Those are the only three ways this can happen. Okay. Oh, yeah. And this is a summary of what we were just seeing. But I think you'll agree that seeing the graphs makes a big difference. It's hard to tell. When you read these three statements, it's kind of hard to visualize what they mean. I think the graphs are awfully helpful in these cases. Now, of course, if we don't have any of these three conditions, that implies that the function is continuous. Um, Now, a function can be continuous over an open interval when it is continuous at every point in the interval. And if it's continuous over the entire real number line, then we say that it is everywhere continuous. Now, discontinuities, interestingly enough, fall into two basic categories. We call them removable and non-removable. What is that supposed to mean? All right, let's take a look. So removable basically means that if we could supply a value here, like let's say we put um, fill in the hole, so to speak, um, then we could end up with a continuous function. This one, there's nothing we can do about it. We can't bridge the gap, so to speak. But here we can apply a point here, and here we can just move it up to the hole. So in other words, by redefining the function, we can get rid of this discontinuity, whereas here it can't be done. Now this one, a good example of this is f of x equals 1 over x. And you can see here, we have an asymptote at the point x equals 0. In other words, the vertical axis is an asymptote. And you see the same problem. There's a gap there. This cannot be removed. Removable means that you could define a new point and get a smooth continuous curve. Here, that can't happen. On the other hand, this one, classic example of one that is removable. Because, in fact, we've seen this one before a couple of times. Oh, actually, no, I'm sorry. This is not the same one. But if you notice, um, there's a discontinuity where x equals 1. So you could, for example, do something like this. In other words, what you're saying is that g of x is defined as this line everywhere except for x equals 1. And then at that point, we'll define x equals 1 to have a value of 2. And so therefore, you're filling in the hole. All right. Now, here's an interesting case. Look at this one. This function is defined in two separate parts. It's as if it was two separate functions sort of glued together. Okay. And so what would that thing look like? So as long as we're x is non-negative, sorry, non-positive, this is x plus 1, which means it's a positively sloped line cutting through 1. And then from this point on, it becomes a parabola. So when we have a function defined in two separate segments like this, it's called piecewise. Now, you might say, well, what a bizarre idea. I've never seen that before. Well, actually, you have. The absolute value function is also piecewise. Okay, and the reason is because as long as x is non-negative, the absolute value is just equal to itself. Over here on this side, though, um, if we're in negative territory, then multiplying x by -1 makes it a positive number to guarantee that the absolute value is never negative. Let me fix that a little here. All right. Oh, that'll have to do. That's fine. Okay, good. Oh no, look what happened over here. Look at that. I didn't know that could happen. All right, hold on 1 second while I fix this mess. So absolute value is piecewise continuous or a piecewise function. Let's see. Now this one, the one that I drew here, um, so what it's saying is that it's continuous within each of these regions. And now here's the interesting part. Both of these, let me just rewrite them again one more time. If I try to evaluate these at x equals 1, not 1, 0, sorry. Um, in both cases, the function equals 1. So that means it's continuous. The entire function is continuous everywhere. There's no gaps. If instead, for example, we had something like this, and in fact, let me just move this down so you can see it better. Yeah, see, that's a different case because so this piecewise function is not continuous everywhere. It's discontinuous at x equals 0 because the value is different on in the two regions. Oh God, this ruined my wonderful graph here, didn't it? Oh, there we go. Um, there we go. That's fine. Okay. Now this one we've seen this before. This is fine. Now the trig functions, at least the sine and the cosine are continuous everywhere. You don't have to show the whole thing. The pattern just keeps repeating itself, but there are no gaps in the sine or the cosine. Now, um, we already went over this earlier. You can have limits from the right and limits from the left. So now it's hard to see here. There's, let me just move it in here into my notes. The limit here, you notice the arrow's pointing to the left, which means that we're approaching from the larger numbers. So while it might sound backwards, it's written like this. So this means that as x approaches c from the right, the limit is L. Okay. Um, then in this case, it's the other way around. So the arrow is pointing to the right, which means we're approaching from the smaller values. And therefore, what we have here is the limit. As x approaches c from the left, looks like it's also L. Okay. Okay, we went through this before, but it's a good opportunity to review it. And these, by the way, these are collectively known as one-sided limits. Okay. Uh, Now look at this one. So the limit of f of x as x approaches -2 from the right is zero. So in this case, we can use direct substitution. Sorry, let me make that a little neater. -2 from the right. Now, if you notice, as we approach from the right, there are no values of x that would lead to any issues like division by zero or an imaginary number. So we can just use direct substitution. And you can see just by looking at the graph that it is zero. But we can't come from this direction because these values of x are not in the domain of the function. So the limit as x approaches -2 from the left is undefined. And similarly over here, we could find the limit as x approaches 2 from the left, +2 that is, with direct substitution. And it's obviously zero, but now because these values are not in the domain, I can't come from the right. So that one is undefined as well. Okay. Now, of course, the overall limit for the function only can exist if these two equal each other. Okay. So in other words, the limit of a function, if the two one-sided limits equal each other. Okay. Oh, by the way, I just realized it's not, you notice how they use the phrase if and only if. What does that mean, if and only if? That's a very good question. We'll see a lot of that in calculus. Um, so let's simplify it a little and write it like this. That means two things. It means that A implies B and B implies A. So the causality goes both ways. Okay. And sometimes you see this abbreviated as IFF. A lot of textbooks do that. Okay. So that means that the causality goes in both directions, or sometimes you see it written like this to indicate that A implies B and B implies A. Or you can think of it as this way. If A is true, then B is true. And if B is true, then A is true. Okay. Then if now again, you notice how they're making a distinction here between closed and open intervals. So let's make sure we remember how this is defined. Meaning that we're including everything in there and the endpoints as well, everything in between plus the two endpoints. Open is the other extreme, where neither endpoint is included. Okay, so sometimes when they're talking about continuity, they make a distinction between a closed and an open interval. So here, what they're saying is that f is continuous over the closed interval if, let's say, I'll see if I can draw a little picture of this. All right, so those are the two endpoints. So f is continuous over AB if it is continuous over AB, open interval AB, and and then there's two more requirements. The limit as we approach A from the right equals f of A, and the limit, um, oh God, there's no room here. I'll move it up here. As x approaches B from the left is f of B. Okay, so that's what it means to be continuous over a closed interval. In other words, we have to specify what happens at the two endpoints. That's really what's going on here. Now, then what we say is that it is continuous from the right at A and from the left at B. That's the terminology we'll use. Okay. Um, Now here's an example. This is just like the one we just did. One minus square root of x, square root of one minus square root of one minus x squared. Okay. Now the domain is only the values between 1 and negative 1, including both endpoints. Okay, we can't go outside that range because we'd end up with a negative square root. So clearly, you can see just by looking at the function. All right, so then we need to check out the endpoints. Okay, so as we approach negative 1 from the right, um, and f of negative 1 Ah, so they equal each other. Okay, good. So um, we say that at the very least, it is continuous from the right, and then we can check. Then we want to check continuous, being continuous from the left. How do we do that? We're coming at one from the left. And we also know that f of positive one, so they equal each other. And then we say that the function is continuous from the left, which means that as we head in this direction, we don't encounter any discontinuities. And the same thing with the continuity from the left. As we go to the right, we don't encounter any discontinuities. So because of these conditions, we can tile that together. So since f of x is continuous over the open interval -1, 1, and the function is continuous from the left and the right, it is continuous over the closed interval 1, 1. All right, let me make that a little bigger. All right, so there we go. Beautiful. All right. So now they've got continuity properties. We're getting towards the end here, but it's getting kind of late. I think I'll tell you what, why don't we stop here with these properties of continuity? And next time we meet, we'll finish this up and then we'll start chapter 2, where we're going to dive into really what I think is the most important concept in calculus, which is derivatives. Okay. And you'll see that in the beginning, we'll define them in terms of limits, but then we'll learn a whole slew of rules that will help us do them directly. And that will take up a lot of our time. That's going to be a huge deal. But here we're just about done with our discussion about limits. And then we can dive into something which to me is more interesting and certainly very important, which is derivatives. Okay, so we'll see you then.